Hello everybody. In this video I'll be covering section 5.4, Law of Cosines. In section 5.3 we saw how to solve oblique triangles using the law of sines in the specific cases of side angle angle, angle side angle, and side side angle triangles. The two types of triangles that we will be solving for in this section are going to be the ones are side angle side triangles and side 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 triangles. There is a sixth type of oblique triangle where you are given three angles, none of the sides, which is actually an unsolvable oblique triangle. To develop the law of cosines, we're going to view an oblique triangle. So I'll draw a standard picture of an oblique triangle with angles alpha, beta, and gamma in the bottom right. So alpha in the bottom left, beta is the top angle, and gamma is the bottom right angle. The side opposite alpha has length A, the side opposite beta has length B, and the side opposite gamma has length C. Just like when we derive the formula for law of sines, I will draw from the top vertex, I will draw a perpendicular line, or a line that is perpendicular to the base, thus creating two right triangles. Okay. The triangle on the left has hypotenuse C. The triangle on the right has hypotenuse A. Let's label the height of both those triangles H. And then now, the triangle on the left, let's say, has base X. And the right triangle on the right, let's say, has base Y. Two pieces of information that we're going to use. We're going to use the Pythagorean theorem to begin with on each of the right triangles. So for the triangle on the left, we know that the base squared plus the height squared has to equal the hypotenuse squared. For the triangle on the right, we know that the base squared plus the height squared has to equal the hypotenuse squared, or a squared. Solving both these formulas for h squared and equating the results is going to give you the equation c squared minus x squared is equal to a squared minus y squared. Now, from the picture below, since x plus y has to equal b, that means that y has to equal b minus x. So I will replace y in my recently formed equation with b. So again, since x plus y has to equal b, looking at the picture in the bottom left, b is the base of the entire oblique triangle. X and y are the bases of each of the right triangles. And subtracting x from both sides, we get y equals b minus x. Substituting that into the previous formula that we had, we get c squared minus x squared is equal to a squared minus b minus x squared. Okay, squaring out the b minus x on the right, c squared minus x squared becomes a squared minus b squared plus 2bx minus minus x squared. So I squared b minus x, and I distributed the negative to the result. Both sides of the both sides of the equation have minus x squared. Adding x squared to both sides eliminates those terms. Okay. I am now going to solve the equation for a squared. So I'm going to eliminate minus b squared and plus 2bx from the right by moving them to the left side. So I'm going to add b squared to both sides, and I'm going to subtract 2bx from both sides. And what we get is a squared equals b squared plus c squared minus 2bx. And there is one final step. Using the picture in the bottom left, if we apply cosine to the angle alpha, we know that cosine is adjacent over hypotenuse, so cosine of alpha ends up being x over c. So x would be c cosine alpha, and therefore the resulting equation, or the resulting equation for a squared then becomes a squared equals b squared plus c squared minus 2bc cosine alpha. This is known as the law of cosines. Okay. And specifically, law of cosines can be used to solve for a side angle side triangle. So, for instance, in the picture on the left, B and C and the angle between them might be known. And in that case, we can solve for A by using the law of cosines. Now, the way to remember the formula is you take a side, like A, and square it. It's going to equal b squared plus c squared, the sum of the squares of the other two sides, minus twice the product of those two sides, b and c, times cosine of the angle either between b and c or opposite a. Okay. In a manner similar to what I just did, I derived the law of cosines for a squared, but drawing a perpendicular to the you can start at any of the other two vertices and draw a picture or a perpendicular to the opposite side of that vertex, and you can use the same argument. But we just derived that the first formula for the law of cosines, and again, this is for this picture as I have on the left. We have alpha on the bottom left with opposite side A. We have beta on top with opposite side B. And we have gamma in the bottom right with opposite side C. So a squared is now b squared plus c squared minus 2bc cosine of alpha. So again, if you're given, in this case, if you're given b and c, and you're given the angle between them, you can solve for a squared. B squared, how does this formula work? You take the sum of the squares of the other two sides, a squared plus c squared, subtract twice their product, and do cosine of the angle between them, which, should be cosine of beta. So you always use, to solve for a side using law of cosines, you always use the two other sides and the angle between them. C squared now would be a squared plus b squared minus 2ab cosine gamma. Okay. And there you have it. Again, just like with law of sines, I don't really memorize the formula so much as I remember it verbally. The same is true here. I think about the given information, and I think about the formula verbally. So any side squared is equal to the sum of the squares of the other two sides minus twice their product times the angle between those two sides. Okay, so here, let's get into some examples. Now, as a rule of thumb, I try to use law of cosines as little as possible. So for side angle side triangles or for side triangles, law of cosines must be used first. If you're watching the video, together with the handout, I have also posted some notes on solving side angle side or side triangles. Okay. So number one, if solving a side angle side triangle, always use law of cosines to find the length of the third side. We'll see shortly if you're solving a side. So number 2, if you're solving a side-side-side triangle, law of cosines must be used to find the first angle. Okay, so you always have to use law of cosines in either of those two cases, whether we're doing a side angle side or a side-side-side triangle. Remember, the previous three types of triangles can be solved with law of sines exclusively. Number 3, when solving a side angle side or side-side-side triangle, you can use law of cosines to find a second angle that'll lead to no issues. But again, you can always just use law of sines to find your second angle once you know a first. Number 4, if law of sines is used to calculate a second angle, using it to find the smaller angle first will lead to no issues. Remember, in a oblique triangle, there's only at most one obtuse angle. Okay, so my general rule of thumb is I never use law of sines to solve for the largest angle, unless I'm forced to use law of sines for our previous 3 types of triangles. Okay, so if I'm finding a second angle, I generally like to find the smaller of the 2 unknown angles first, because that will be an acute angle and you will not have any issues using law of sines there. Number 5, if law of sines is used to calculate a second angle, which ends up being the largest angle, okay, it's opposite the longest side, the angle will most likely be obtuse, not always, and to actually find that obtuse angle, when you solve for the angle using law of sines, it's actually going to be acute when it's supposed to be obtuse, and you need to subtract that result from 180. So in that case, I try to avoid the situation in number 5 happening. That's why I always revert you back to step 4. If you're going to find another angle, make sure you are solving for the smaller of the 2 remaining angles so that you have no issues. You have to use arcsine to find that angle if you use law of sines, and the range of arcsine is only angles between 0 and 90 degrees, essentially. So if you're using law of sines to solve for an obtuse angle, you're going to get the wrong answer. Okay, so into some examples we go. Okay, so first we solve a side angle side triangle. We're going to find A, beta, and gamma for an oblique triangle where the side B has length 3, side C has length 8, and alpha is equal to 70 degrees. Again, as usual, I will draw a picture of a triangle, except for this is not representative. I just use this for labeling. So alpha is 70, that's the angle in the bottom left. Okay, the opposite side from alpha is A. We don't know beta, and we don't know gamma. And we know the side opposite gamma C is 8 units in length, and the side opposite beta is 3 units in length. Now, what I want you to notice is the situation that we have. This is a side angle side triangle. Okay, so I know 2 sides, and I know the angle between them. That is a perfect situation for law of cosines because the formula for the length of A using law of cosines involves those 2 other sides and the angle between them. Okay, so what's the formula now for law of cosines? A squared is b squared plus c squared minus 2bc cosine of alpha. And we just so happen to know b, c, and alpha. Okay, now you can take the square root of both sides, and technically if you took the square root of both sides, you would need a plus or minus, but since we're talking about length, the minus can be omitted. A is going to be the square root of b squared plus c squared minus 2bc cosine alpha. And now I'll just plug the known values from my picture into the formula. A then is now the square root of b squared, or 3 squared, plus c squared, or 8 squared, minus 2 times 3 times 8, and then times cosine of the angle between those two sides, which is cosine 70 degrees. I'm going to round my answer to 2 decimal places. Actually, you know what I'm going to do here? I'm going to round it to 4 decimal places, and I'll round all my final values to 2 decimal places. And making sure that our calculator is in degree mode, since we're working with degrees, we get 7.5222. So 7.5222. And again, I'm rounding all of these intermediate values to 4 decimal places to eliminate rounding errors if I want all my final answers to be rounded to 2 decimal places. Okay, so now I know A. And one thing I notice about my picture right away that doesn't make sense is that I've drawn beta as an obtuse angle. And the length of the side opposite beta is 3, and clearly that is longer than the side of length 8. If I was going to draw a more accurate picture in this case, which I probably should, I'm going to make beta a acute angle. There we go. So alpha was 70 degrees. There's beta. I think I'm still off right here. This is really bad. Here we go. There we go. Let's make that side long. There we go. I like that better. It makes a lot more sense to me. Okay, so we know the length of the 3 sides. Now we need to find the other 2 angles. Now, here's where, if you go to my handout, on my guidelines, and you look at number 4. Okay, now again, law of sines. When you use law of sines to find an angle, you have to use arcsine. Okay, so if you're using law of sines to find an obtuse angle, when you actually use arcsine to find the angle, the range of arcsines between 0 and 90 degrees. You're not going to get the correct angle. So I'm going to use law of sines to find a second angle, but I'm going to find the smaller angle first. Okay, so in that case, since the side that's opposite beta is 3 and the side opposite gamma is 8, that means beta has to be the smaller of the 2 angles remaining. So let's find beta first. So we're going to use law of sines. In the bottom left, sine of beta over 3 now equals, the only other pair of side and opposite angle we know are alpha and A. So we can set that equal to sine of alpha, or sine 70 degrees, and divide by A, which is 7.5222. So this is why I've rounded A to 4 decimal places, because that value is being used in this calculation. So I'm already creating rounding error. So in order to minimize rounding error, if you have to round all of your values to 2 decimal places, round any intermediate values to at least 2 more to avoid those rounding errors. Now beta, you can multiply both sides by 3 and then take arcsine of both sides. Beta will be sine inverse of 3 sine 70 divided by 7.5222. Now, I can round this to 2 decimal places because I'm going to use, once we know this angle, we can find the third by doing 180 degrees minus the previous 2. So now beta, it's approximately 22.01 degrees. And actually, let's do this. Okay, so beta is 22.01 degrees. Now in black, I'll write the next part. That means gamma has to be 180 degrees minus the value or the measure of the other 2 angles. And therefore, gamma is approximately 87.99 degrees. Okay, and I made a mistake when I wrote beta was 22.01 degrees. I should have used the approximately symbol. Okay, so now I have my three values. And again, I should probably round A to 2 decimal places. A is approximately 7.52. Beta is approximately 22.01. And now gamma is approximately 87.99. Okay, wonderful. Okay, so we'll do one more example of a side angle side triangle before we do an example of a side triangle. So again, we'll draw a picture here. And again, I'm going to start out by drawing it not so representative. Let's maybe do this. I'll just make everything look acute, even though that might not be the case. So the angle on the bottom left is alpha. The angle on top is beta. The angle on the bottom right is gamma, which is 20 degrees. The side opposite alpha is A, that's length 8. The side opposite beta is 3. And the side opposite gamma is unknown, so that value is going to be C. Now again, in the picture, how do I know I need to use law of cosines first? I have two sides, and I know the angle between them. So I can use law of cosines to solve for C. Okay. Now, C squared is B squared plus C squared minus 2AB cosine of gamma. Okay, so I just set all that formula. But since the formula is C squared equals, I'm just going to start out by taking the square root of both sides right off the bat. C is the square root of B squared plus A squared minus 2BA, or AB, it doesn't really matter. Or I can do A squared plus B squared. 2BA times cosine of the angle between them, which would be gamma. But by them, I mean gamma is between the sides of lengths A and B. So now C has to be the square root of B squared, or 3 squared, plus A squared, or 8 squared, minus 2 times 3 times 8 times cosine of gamma, which is 20 degrees. Okay, and again, I'm going to round this to 4 decimal places. I'm going to round my final answer to 2 decimal places. Rounding C to 4 decimal places, I get 5.2815. Okay, now that I have a third side, I can solve for one of the other 2 angles. Now, you can use law of cosines to solve for an angle because the range of arc cosine is 0 to 180 degrees. So there's no issues using law of cosines. I personally find using I personally find using law of sines easier. However, I'm going to do it in this case just for an example. So I would use law of sines to solve for beta in this case. But just to show this to everybody, I am going to use law of cosines. So again, you can always use law of cosines or law of sines to solve for a second angle. You just have to be careful that if you use law of sines, you solve for the smaller of the 2 remaining angles. Now, the law of cosines that involves beta is actually B squared equals A squared plus C squared minus 2AC cosine beta. Now, you can solve for cosine beta by subtracting A squared and C squared from both sides, and then dividing by minus 2AC. What you end up getting is you get A squared plus C squared minus b squared all over 2ab. Sorry, ac. My bad. So you start by subtracting a squared and c squared on both sides and dividing by minus 2ac. And if you move the negative in the numerator and distribute, you get a squared plus c squared minus b squared over 2ac. Okay, so in the numerator, all the terms are a squared, c squared, and b squared. Just remember that the negative goes with b, and then you divide by 2ac, because the way I remember it is the two terms in the numerator that are positive, that have positive coefficients, correspond to a and c. Now, you can take arc sine of both sides, or arc cosine of both sides, and then we can plug in all of those values. Because we do know a is 8, we do know c from the previous step, and we know b is 3. Okay, so beta is now going to be arc cosine of, now it's a squared plus c squared, so a is 8, so you get a squared plus our c squared, which is our 5.2815 squared, minus b squared, or minus 3 squared, all divided by 2ac. So 2 times 8 times 5.2815. Okay, and again, the other reason I like to use law of sines is it's just a much more simple and elegant formula than law of cosines. So when I calculate beta now, and I round it to 2 decimal places, we get, okay, you end up getting 11.2 degrees approximately. One other comment that I want to make, if you did use law of sines to solve for this angle beta, you're going to notice that the exact value that when we solve for beta, using law of cosines, is actually slightly different than the value you would get using law of sines. The reason for this is that arc sine and arc cosine are going to produce different amounts of error because we've rounded the side of length c. Okay, so the thing is if you use exact values to make calculations, you get precisely the same values. But when you use arc cosine to solve for an angle, you're going to get a technically different value than when you used arc sine. Okay, they're going to be the same up to 2 decimal places. This is why I had you round c to 4 decimal places, so that we lessened the impact of rounding errors. Okay, and then finally, we can solve for the angle alpha. We know that alpha is 180 degrees minus the 2 other known angles. And what we get, alpha ends up being approximately 148.8 degrees. Okay. And there we go. So my picture was a little off. In my picture, I have alpha as labeled as being an acute angle when obviously it is not. It's far from an acute angle. And of course, actually at the bottom, why don't I round c to 2 decimal places? I get 5.28. Okay, so when you draw the pictures, they're just guides to help you. I don't really, obviously when you draw them, they're not always going to be accurate. That's okay. But in this case, so we first solved for c and got 5.28 to 2 decimal places. Then we solved for beta and got 11.2. And then we solved for alpha and got 148.8. Okay. So again, when I found the second angle, I didn't need to use arc cosine. In fact, I would have preferred to use arc sine. I was just exemplifying how you would go about using arc cosine. So the only time you have to use arc cosine to solve for an angle is if you are solving a side-side-side triangle, which is what we are now going to tackle. So this will be the last example. And let's see, we're going to have 3 known sides this time. Since this is a side triangle. And I'm going to try my best to make, now A is the longest side. Okay, so what I'm going to do is I'm going to draw alpha like it's obtuse, even though it may still end up being acute. I'm not really sure. So I've got alpha at the bottom, beta in the top left, and gamma in the bottom right again. The side opposite A is 9. The side opposite gamma is 7. And the side opposite beta is 4. And we're going to use, well, we have no other choice but to use law of cosines to solve for an angle. And okay, now law of cosines must be used to solve for the first angle. And here's what I generally like to do. If you use law of sines, or, when we use law of sines to find the second angle, because that's what I prefer to do, right? We don't really like using law of sines to find the largest angle, because it might be obtuse, and we'd have to use arcsine, which only spits out angles between 0 and 90 degrees. So for that reason, I'm going to probably just solve for alpha first, right? It's going to be the largest angle. It might be obtuse. I'll just get that one out of the way first. Okay, so the formula for cosine of the angle alpha is going to be, well, you know what? I'm just going to start with the law of cosines that involves a squared, because cosine of alpha is in that formula. So remember, a squared is b squared plus c squared minus 2bc cosine alpha. Solving for cosine alpha, you get b squared plus c squared minus a squared over 2bc. Okay. And then alpha, therefore, taking arc cosine of both sides, would be cosine inverse of, and now I can just plug in my values for b, c, and a. So it'd be b is 4, so I get 4 squared, plus c is 7, so 4 squared plus 7 squared, minus a squared, or 9 squared, divided by 2 times b times 7. So the denominator is 2 times 4 times 7. And I will round this to 4 decimal places because I'm going to round my final answers to 2 decimal places. So any intermediate calculations, I'm going to carry 2 extra decimal places. And alpha ends up being, doing cosine inverse of the quotient inside the parentheses, we get 100 and 06, so 106.6015 degrees. Okay, so I was right that angle was most likely the one to be obtuse. It's larger than 90 degrees because that's the angle opposite the longest side. Okay, now again, to find a second angle, I have to either use law of sines or law of cosines. So I was stuck with using law of cosines for the first angle, but now I can use whatever I want when I solve for the second angle, and I'm just in favor of law of sines. It's in my opinion, simpler. It's a little easier to set up. So now what I can do is I could say solve for beta. So using law of sines, sine of beta divided by 4 equals sine of alpha divided by the length of its opposite side of 9. So that's the only angle that I can really use, because up until this point, that's the only angle that I know, right? So I have to do sine of alpha over 9. Okay, solving for sine of beta first, multiplying both sides by 4, and then taking arc sine of both sides. Beta is sine inverse of sine of 106 point, oh, I'm missing the 4. So beta is 4 sine 106.6015 divided by 9. And beta therefore, is approximately, and I'm going to round this to 2 decimal places. I get 25.21 degrees. Okay, so there's beta. Now I can find gamma, because gamma is 180 degrees minus the first 2 angles. And I'm just going to round alpha to 2 decimal places to make this calculation. And what we get then for gamma, it's approximately 48.19. Okay. And there's gamma. And I'll just round alpha now to the 2 decimal places. So alpha is approximately 106.60, or just 106.6 degrees. There's my 3 angles. So there was 3 examples of how to solve oblique triangles with law of cosines. The first 2 examples were side angle side triangles, and the third example was a side 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 triangle. In either case, you had to use law of sines first to either solve for the third side in a side angle side, or to solve for one of the angles in the side 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 triangle. Once you use the law of cosines once, you never have to use it again, unless you're going to be using law of cosines to solve for a possibly obtuse angle. So for that reason, if I ever need to find a second angle, I prefer to use law of sines and solve for the smaller of the 2 remaining angles. So thanks for watching the video. Take care, everybody, and I hope to speak with all of you soon. Thank you. Bye-bye.